Right, so good afternoon to everyone, good afternoon to all, and welcome to MoyoMath. We're going to start. We're going to start shortly. Just give persons time to have a pop onto the live. So in a few minutes, we get started. Probably in about the next 2 to 3 minutes. All right, so good afternoon to all, and welcome to MoyoMath. Of course, we know that this Tuesday is an important exam. This Tuesday is your AddMath examination, and we want to ensure that we're ready for this exam on Tuesday. So today, we want to use today to do a quick review of topics we expect to see in sections 1 and 2 of the exam paper, and we also want to, tomorrow, we want to look at sections 3 and 4. So we know sections 1 and 2, sections 1, you focus on the algebraic component, so remainder factor theorem, dealing with quadratics, dealing with APs and GPs, dealing with everything under the umbrella of quadratics, from inequations to completion of squares to types of roots. So we want to ensure that we are clear on these important topics. Logarithms, we want to ensure we are clear on logs, we are clear on as well surds, and we are clear on solving equations in index form, exponential equations. Section 2, you have topics such as the equation of a circle, which is normally the first question you see in section 2 of the exam paper. You also have sectors, you have vectors, you have trigs. So we want to cover some of these topics today in both sections 1 and 2, so we can put ourselves in a good position to be prepared for this exam on Tuesday. All right, but before we get started, I like everyone to subscribe to the channel, so make sure you press that subscribe button. So let's make sure we subscribe to the channel before we get started. And remember, the session, we want it to be interactive, so if anyone has any questions, feel free to ask your questions. My assistant is here to assist. All right, so they will relay the questions to me and I will answer accordingly. So keeping in mind, we may want to spend, say, about 3 to 4 hours. So we'll see how quickly we can get all covered within that time. Okay, so let's jump into it. So we're going to start off with remainder and factor theorems. You want to start off a remainder and factor theorem, and just to ensure that we can recall what we know remainder and factor theorem is all about. So you have your remainder and factor theorem. So remainder and factor theorem, and let me know by a show of thumb if you're seen on the board. So have we seen on the board? Show of thumb. So have we seen what is written on the board? Show of thumb. Yeah? Good. Nice. Good. So we know when it comes to remainder and factor theorem, we want to make sure we understand the difference between the two. Remainder and factor theorem, from a simplistic explanation, you will have your, say we have 15, which is your dividend. You have, say for example, 4. 4 is your divisor. And if I divide 4 into 15, we know that 3 by 4 will give us 12, and 12 from 15 gives us a remainder of 3. So this 3 here, of course, will be known as your remainder. And the 3 on top here, it's known as your quotient. So when we divide our divisor into our dividend and we get a remainder that is not 0, then this will fall under what we call the remainder theorem. So we want to make sure we're clear on, when we talk about remainder theorem, it is one where the remainder is not 0. Okay? So this is your remainder theorem. So we know that your dividend is equal to your divisor multiplied by your quotient plus your remainder. This is what the dividend is equal to. The dividend is 15 is equal to your divisor 4 times the quotient 3 plus the remainder 3, and 4 by 3 is 12 plus 3 gives 15. Okay, so just understanding the basic concept, but this is a simplistic explanation, but of course we have to learn how to divide one expression into another. So we have as well, so this is your remainder term. So remainder term. You also have your factor term. So the factor term, the same application, but this time, if I divide, say, 3, which is my divisor, into 15, which is my dividend. So of course, 3 divided into 15 will give me an exact value. Yeah, 3 into 15 is 5. 5 by 3 is 15. And 15 minus 15 gives me what? 0. So when the remainder is 0, this is said to be the factor term. So when I divide my divisor into my dividend, I know that my remainder for the factor term will always be 0. So something, we need to make sure we understand. So I know for the remainder term, your dividend, of course, is again equal to your divisor multiplied by your quotient plus the remainder. But again, for the factor term, the remainder is always 0. So this is your factor term. So understanding the basics of both remainder and factor term, we're going to treat with dividing one expression into another. And we're going to look at some past paper questions to highlight it. Understanding if we have to find the remainder for both terms, there are two very important methods we are going to be introduced to as we go through the questions, and we need to apply when we're doing these questions on Tuesday, because you're going to see a remainder factor term in the exam. That's guaranteed, right? So we need to be familiar with one. There is the substitution method. So the methods we need to familiarize ourselves with to find the remainder for both terms. You have the substitution method. And 2, there is the long division method. So before we get into the questions, just to quickly touch on some key points before we get into the question. So understanding what is the factor term, understanding what is the remainder term. The remainder is not 0. It can be a positive or negative number. The factor term, the remainder is always 0. And to find the remainders, we can use two methods. You have the method of substitution. You also have the method of long division. Yeah? So let's look at some questions to highlight our understanding of the remainder and factor term. All right? So let's get into some questions. So I'm going to erase this half of the board. Now if we have here right, so this is from June 2022, and this here is a question involving your remainder factor term, and let's see which one is applicable here. It says here, when the polynomial expression, and the polynomial is an algebraic expression, 2x cubed minus 3x squared minus cx plus d is divided by x plus 1 and x minus 2, the same remainder of 64 is obtained. So when we take our two divisors known as the linear factors, good, so those are also linear factors, when we divide them into this cubic polynomial, we are going to get remainders. As I showed you, if you take a divisor, divide it into your dividend, you're going to get a remainder, you also get a quotient. So we're going to get a remainder that is what? 64. But in this question, our cubic polynomial, we have two unknowns in that cubic polynomial. One is c and the other is d. And the objective of this question is to find the value of c and of d. So we want to find c and d. Okay? So to find c and d, and always remember in mathematics, AddMath, anytime you have to solve for two unknown quantities, the objective is to create a pair of equations which you're going to solve simultaneously. Alright? So we know if we have to find those unknowns c and d, we have to create a pair of equations. So how are we going to create the pair of equations to find the unknown quantity? So to create the pair of equations, we're going to introduce the two methods. One of the two methods that I showed earlier. We're going to introduce the method of substitution to help us to create these two equations and hence solve our pair of equations to find the unknown c and d. So let's create the pair of equations using this method of substitution and understanding how to apply this method. So we have here so this is certainly the first question you're going to see in the exam. Remember, when you look at past papers, functions and relations would have normally been the first, but there's no functions and relations will no longer be tested on the paper. All right, so most likely they're going to begin with remainder factor theorem. All right, so let's treat with it. We have here this polynomial. So most times, we name the polynomial, we can call it P of x, you call it f of x, whatever you choose to call it, is equal to 2x cubed minus 3x squared minus cx plus d. So this is one, that's your polynomial, which I've called P of x. You could call it f of x, you could call it whatever you want of x. So it is a cubic polynomial. Now it is divided by this divisor x plus 1 and x minus 2, and they both will give the same remainder of 64. So based on that information, we can create two equations. So let's treat with the first linear factor, equal x plus 1 and x minus 2, we call them linear factors. Just remember that as well. Get familiar. So we're going to take that first linear factor and divide it into our dividend to get the remainder of 64, but using the substitution approach. And how is this done? We're going to let our divisor x plus 1 be equal to 0. And therefore x will be equal to negative 1. Now, of course, when we substitute this, and this is where the substitution approach will come into play. When I substitute this value of x into my cubic polynomial, I am going to get a remainder of what? 64. Because when both divisors are divided into that dividend, that cubic polynomial, otherwise known as a dividend, we are going to get a remainder of 64. So let's show how we're going to set up an equation by me substituting this value of x into that cubic polynomial to get a remainder of 64. This is what's going to happen. It becomes 2 open brackets negative 1 cubed minus 3 open brackets negative 1 squared minus c open brackets negative 1 plus d. So when I take this negative 1 and substitute into my cubic polynomial, I am going to get a remainder of 64. And that's one equation we're going to, of course, simplify and use when we have to solve our pair of equations simultaneously to find c and d. So it's a simple case of substitution. So what's going to happen? Let's simplify this equation. This becomes negative 1 cubed, of course, will be negative 1 by 2 is negative 2. Negative 1 squared will be 1. 1 by negative 3 is negative 3. Negative c by negative 1 will be positive c, plus d is equal to 64. This becomes negative 2 subtract 3 will give us negative 5, plus c plus d is equal to 64. And now what I can do is make c plus d the subject. I can remove negative 5 by adding 5 to both sides. So it becomes 64 plus 5. So c plus d is equal to 69. And that there is one equation. So I've obtained one equation based on the fact that my divisor can be divided into my dividend to get a remainder of 64. And use a method of substitution to help us to create this initial equation, which we'll use in the process to find c and d. So let's look at another, because remember we have to create two equations, right, to get c and d. So far, let me see by a show of thumb. Are we all clear on what I did to get this first equation? Let me see by a show of thumb, quick show of thumb. Are we all clear? So quick show of thumb, thumbs up. Let me see those thumbs up. Yeah? Good. So now let us use the same. Let me take my divisor, which is my other linear factor, x minus 2, and let me divide it into that cubic polynomial as well to also get the same remainder, setting up an equation in the process. So what am I going to do? I am going to let x minus 2 be equal to 0, and therefore x is equal to 2. And what I'm going to do, same process as I did with the first linear factor x plus 1, I'm doing the same for x minus 2. I let x minus 2 be equal to 0, x is 2. I'm going to substitute 2 now into my what? Into my cubic polynomial. So it becomes what? 2 open brackets 2 close brackets cube minus 3 open brackets 2 squared minus c open brackets 2 plus d, and this here will also be equal to, it will also give a remainder of 64. So that will be equal to 64, because when we read the question carefully, when we divide our linear factors, which are x plus 1 and x minus 2 into the polynomial, the remainders are 64. So we're showing here, when we be using this method of substitution, when we divide that divisor into our dividend, we're going to get a remainder of 64. Divisor being your linear factor, dividend being your cubic polynomial. So let us simplify this to get another equation. This becomes 2 cubed will be 8. 8 by 2 will be 16. 2 squared is 4. 4 by negative 3 is negative 12. This will be minus 2c plus d is equal to 64. I can further simplify. This becomes 16 minus 12 will be 4. Minus 2c plus d is equal to 64. And what I'm going to do is make sure my unknowns c and d are on one side of the equal sign, and of course I'll put my constants on the other. So this will be negative 2c plus d is equal to 64. Subtract 4. So I subtract 4 from both sides. And what's going to happen here? I'm going to further simplify, so I'll just close down the PowerPoint so we can utilize the space to continue. So this becomes what? This becomes negative 2c plus d is equal to 60. So creating two equations. So this is my second equation. So I have my first equation, I have my second equation. Keeping in mind, if we have to solve for two unknowns, you go in that AddMath exam on Tuesday, you see a remainder factor term, they ask you to solve for two unknown quantities. You know you have to create two equations, a pair of equations, which you'll then have to now solve simultaneously to find for the unknown quantities. And this is what we're going to do now. So we have two equations. One is c plus d is equal to 69, and the other is minus 2c plus d is equal to 60. So I have my two equations, label 1, label 2. Let's solve them simultaneously. So you know simultaneous will always come into play when it comes to most of the questions in AddMath. So let's use the elimination method. You can use substitution too. Let me eliminate d. It's easy to eliminate d because the d variables are the same. So it's easy to eliminate d by simply subtracting both equations. And what I like to do is put my subtraction sign in between. So we'll know that we're subtracting our terms involving c, we're subtracting our terms involving d, and we're subtracting our constants. So I draw my line and let me subtract. We know that d subtract d is automatically 0. That will cancel out. And what we see here vertically, I always encourage students to write it horizontally. Some students can work it out in their minds one time. But let's write it horizontally. This will be c subtract negative 2c, and we make sure we put negative 2c in brackets to separate the two signs, is equal to 69 subtract 60. So we're going to get here c, a minus by a minus is a plus, so we remove the brackets, plus 2c is equal to 69 minus 60, which is obviously 9. We're going to get here c plus 2c will give us 3c is equal to 9. And what we can do is divide both sides by 3. And we're going to get c is equal to 3. So we have found our value of c. Yeah? So a simple case of understanding this whole process of the substitution approach or method to help you to find the remainder, creating an equation, and solving simultaneously. So after finding c, let's go find d. So what we're going to do, we're going to substitute C equal to 3 into any one of the original equations. You pick them, 1 or 2, doesn't matter. So I'll put it into equation 1. Equation 1, we have C plus D is equal to 69. And where I see C, I'm going to replace it with what? 3. So this is 3 plus D is equal to 69. And therefore, I can solve for D by subtracting 3 from both sides. So this is 69, subtract 3, and therefore D is equal to what? D is equal to 66. So you would have found your value of C and D? Straightforward. So you can state here, therefore, C is equal to 3 and D is equal to 66. Alright, so looking at one question here involving remainder factor theorem. Right, the whole understanding of this process. Alright, so let me see that show of thumb. Are we all good? We're clear on what was done here? Creating two equations, solving them simultaneously. Everybody we're clear? Let me see that show of thumb. Everybody we good? Remember, if you have any questions, don't be afraid to ask the questions. Yeah? Everybody's good? Nice. And don't forget to ensure that you subscribe to the channel. Ensure that that you share the link with your friends so they can jump on the live and be a part of the exercise to prepare for the examination. All right, so make sure you share. So let's look at another question. It says here, and let me put it on the board. So if you want to take a screenshot, of course you're going to see the video will be posted to YouTube, so you can look at the video again. But in the interim, if you want to take a screenshot, you can do so. Yeah? So you can have the solutions. So I'm going to erase this side. And let's look at another question. Right? This one is from June 2021. Determine the remainder when that polynomial is divided by x minus 1. So they want us to find the remainder. So again, this is your what? So you see this in the exam, how you treat with it. This is your dividend. This is your linear factor, which is your divisor. And if you have to find your remainder, you're going to divide your divisor into your dividend. And what you can use here is a method of substitution to find out what's the remainder. That's all. Just a method of substitution to figure out what is the remainder. So let's go figure out what is the remainder. So we have here so you have your polynomial. So you see sometimes they'll give the polynomial a representation. They'll use f of x, p of x, g of x, whatever of x, right? So you have this polynomial here. F of x is equal to ax cubed plus 7x squared minus 7x minus 3. And it is divided by x minus 1. What's the remainder? So what do we do to get the remainder? What do? We always begin by taking the linear factor, otherwise known as your divisor. We're going to let that linear factor be equal to 0. We're going to get the value of x, which is 1. We're going to take this value of x now and substitute it into your cubic polynomial. Into that polynomial. Given polynomial is another word for algebraic expression. And what we will do is get a representation for the remainder. That's all. So let's see what we're going to get as a remainder. So I'm going to now take 1 and substitute it inside here. But sometimes what you can write f of 1. You know that from functions, if you put f of 1, it means you're going to substitute 1 inside here. So when you see x, you're going to replace it with 1. So this becomes a times 1 in brackets cubed plus 7, 1 in brackets squared, minus 7 times 1 minus 3. Which will break down to what? 1 cubed is 1, 1 by a is a. 1 squared is 1, 1 by 7 is 7. Negative 7 by 1 is negative 7 minus 3. And when we simplify that, what we're going to get? A 7 minus 7 is 0. So you're left with a minus 3. So you see a minus 3, this is the remainder. The remainder is in terms of a. Sometimes if a is a number, obviously, and you do the substitution, the same approach, we're going to get the remainder as a value. In this case, the remainder, when we carry out our steps, don't be confused if you see a minus 3, the answer for the remainder will be in terms of a. Alright, and that will be your remainder. Alright, so that is it for that part of the question. Easy, 2 marks in the bag. Everybody be clear on that? We clear on what I did to get a minus 3 as your remainder? Everybody be good? So let me see that show of thumbs. Thumbs up. Thumbs up. We got a minus 3 as a remainder. Thumbs up. Yeah, nice. So we have now the next part of this question. It says, if the remainder when f of x is divided by x plus 3 is equal to the remainder in a part 1, find the value of a. Again, what they want you to find in part 2, an unknown, they want you to find a. Just remember, anytime in maths, AddMath, you have to find an unknown quantity. You create an equation. If you have to find 2 unknown quantities, you create 2 equations and you solve them simultaneously. So let's read the question. If the remainder when f of x, that cubic polynomial, is divided by x plus 3, so we're going to take this linear factor, divide it into this cubic polynomial, carrying out the same substitution approach we just learned, and we're going to get the remainder, and we're going to take that remainder when we divide x plus 3 into that cubic polynomial, and we're going to put it equal to the remainder we got in part 1, which is this remainder here. Alright, so we're going to take the remainder, when we take x plus 3, divide it into the polynomial, put it equal to this remainder, create an equation, and let's solve for it. Alright, and let's see what's going to happen. We're going to say what? So, part 2, this is part 1. Part 2, again, same process. We're going to let x plus 3, which is your linear factor, be equal to 0. X will be equal to what? Negative 3. Subtract 3 from both sides. And what am I going to do? I'm going to substitute negative 3 into the what? Into the cubic polynomial. So I'm going to get f of negative 3 becomes what? A negative 3 in brackets cube plus 7 negative 3 in brackets squared minus 7 negative 3 in brackets minus 3. And when we simplify that, what are we going to get? Negative 3 cubed will be negative 27. Negative 27 by a is negative 27a. Negative 3 squared is 9. 9 by plus 7 is 63. Negative 7 by negative 3 is plus 21 minus 3. So when we simplify that, what are we going to get? We're going to get negative 27a. We know 63 plus 21 will give us 84. And 84 minus 3 will give us plus 81. Yeah? So that's the remainder we're supposed to get when we divide that linear factor, otherwise known as your divisor, into a cubic polynomial. That's the remainder we're going to get. But then, let's make sure it's all good. Negative 27a. So what I want you all to do on the live, make sure you double check, make sure my substitution is correct and my calculations is correct as well. Any errors, you make sure you point it out. Alright? So this is 963 plus 21 minus 3. That is 84 minus 3, 81. Alright? Good. So now, let's continue to find a. We're going to take the remainder we got when we divided x plus 3 into the polynomial. And put it equal to the remainder we got in part 1. So let's put the remainders. Let me just close down the PowerPoint there. So we're going to get what? This becomes, so therefore, negative 27a plus 81 is equal to a minus 3. And let's solve that equation. This will be what? We're going to place all terms with a on the left-hand side, preferably. Negative 27a plus a comes across as negative a. And let's put all numbers on the right. This is negative 3. Positive 81 comes across as negative 81. We're going to get negative 27a subtract a will be negative 28a, and negative 3 subtract 81 will give us negative 84. Yeah? And what we're going to do now is find a by dividing both sides by negative 28. So a is equal to what? When we divide 28 into 84, we're going to get positive 3. Yeah? So the value of a is 3. Yeah? Simple and straightforward. So making sure we understand that substitution approach. You know, you can well see a question in the exam on Tuesday with remainder factor term where that has to come into play. You just simply let the divisor be equal to 0, substitute it into the polynomial, put it equal to whatever remainder is given. Sometimes if they mention that the polynomial is a factor, so that the divisor is a factor of the polynomial, then note the remainder will be 0. So when you substitute the value of x into your polynomial, you're going to put it equal to 0. That is if they mention that the linear factor or the divisor is a factor, right? So normally you'll see factor, that word factor. If it's a factor of the polynomial, then you're going to see that happening. All right? So let's look at just one more example remainder factor term, and then we will move on to some indices, surds, logarithms. Let's make sure we understand indices, surds, and logs. So we'll do some of that, and from there we move on to quadratics. Let's make sure we understand everything under the umbrella of quadratics, and then we'll look at some APGPs, and that will be it for section 1. And we move on to section 2 next. All right? Yeah? So. Oh, finally. Oh. Yeah, finally fix it. Finally. Right, I'm glad you'll observe that. Nice. Good. You see, I mean, you know, when you normally start something, you'll have little teething problems, but eventually you'll get it right. Yeah? All right, so next. Let's look at this. If we have this example, now sometimes you can see a question like this in the exam. Right, this is from June 2019, and they want us to determine all linear factors of f of x. What are all linear factors of f of x? So f of x is this cubic polynomial we have here. 2x cubed plus 7x squared plus 3x. And they want us to determine what are all the linear factors. Okay? So, what do you mean by that? So, when you have this cubic polynomial, we can represent that cubic polynomial as as a product of linear factors. So you know, normally if you have a quadratic and you have two sets of factors and you multiply the two sets of binomials and you multiply to get back the quadratic expression. Similarly, you have this cubic polynomial, and what you want to do is to express this as a product of factors. Okay? And we want to determine what are these linear factors. What is this and what is that? What are the linear factors? And sometimes it can be more than one factor. Sometimes when it's cubic, you'll see like about 3 factors. So let's see how we treat with this question here. This is from 2019. So normally, with questions involving remainder factor term, they will give you one of the linear factors, and when they give you one of the linear factors, you can use that linear factor to help you to find the others. And sometimes a method of long division can come into play. You have other methods, but you can use a method of long division to help you to find what the other linear factors are. But sometimes they'll give you a question like this one, where there's no linear factor to really start off with. Okay? So they didn't give you a linear factor to start off with to help you to get the other linear factors. So what you have to do to find your first linear factor, you have to implement a method of trial and error. Good? So using a method of trial and error to help you to find that first linear factor. This is one question that will require you to use that trial and error process. So what you can do, you start off with let x be equal to 1, And what you want to do, because they're linear factors, when I substitute 1 into that polynomial, I must get 0. Once I get 0, it means that it is a linear factor. So when I put 1, you can start off with 1. If it doesn't work, you go with -1. If that doesn't work, you go with 2. You go with -2. You keep substituting until you get 0. And when you get 0, then we can recognize what's the first linear factor. So you could say here, when x is 1, substitute 1 inside there. You're going to get what? F of 1 becomes 2 times 1 cubed, 7 times 1 squared, 3 times 1. Let's see if we're going to get 0 here. Clearly not. This is 1 cubed, which is 1. 1 by 2 is 2. 1 squared is 1. 1 by 7 is 7. 1 by 3 is 3. We're going to get, which clearly is not 0. You could try -1. Also, we wouldn't get 0. I think when I was doing this question, I think when you substituted, so when you do all those substitutions, I'll try, I think it was up to 3. Let me try 3. So let's try when it's 3. So let x be equal to 3. So you, of course, you will have to try until you get 0. So when x is 3, let's see what we're going to get. F of, let me put -3. I think it worked with -3. Let's see. F of -3 becomes 2 times -3 in brackets cube plus 7 -3 in brackets squared plus 3 -3 in brackets. So using a method of trial and error here to figure out what's the first linear factor. All right? So again, you start with 1. If it doesn't work, you try -1. If that doesn't work, you try 2. If that doesn't work, you try -2. If it doesn't work, you try 3. You try -3, right? And let's see if we're going to get 0. This will be -3 cubed is -27. -27 by 2 is -54. This will be -3 squared is 9. 9 by +7 is +63. And 3 by -3 will give us -9. Yeah? And let's see what we're going to get here. This will be, I can say, -54. And +64 minus 9 will give me what? Plus 63, sorry, minus 9 will give me +54. And -54 plus 54 is 0. So you see, when x is equal to -3, we're going to get 0. All right? Which will tell us x substituted into that function gave us or that polynomial gave us a remainder of 0. And what it will imply now, therefore, x plus 3. So -3, bring it over on the left of the equal sign. Therefore, x plus 3, that is a first linear factor, is a factor of f of x. So that's your first linear factor. They didn't give us 1. Normally they'll give you 1. They didn't give us 1. So you have no choice but to implement a method of trial and error. Yeah? Right? So trial and error. So what you're going to do is use this method of substitution and figure out what is the first linear factor. Everybody be clear now I got that first linear factor? Let me see a show of thumb. Show of thumb. Clear how I got that first linear factor? Yeah? Using that method of substitution. So you're using trial and error. Yeah? Good. So if it's x is equal to -3, you bring -3 over on the left, it means x plus 3 is a factor of f of x. Alright? So having found that first linear factor, remember this cubic polynomial, which is your 2x cubed plus 7x squared plus 3x, will have a number of linear factors, right? So this is one of them. So we have found the one. So we want to determine what are the other linear factors. Yeah? What are the others? So to find the other linear factors, this is where we can use now a method of long division. So you can use the long division approach to help you to figure out what are the other linear factors. So let's use the long division approach. So I'm erasing here. So I'm going to divide, take my first linear factor that we got, which is x plus 3, and I'm going to divide it into my cubic polynomial given 2x cubed plus 7x squared plus 3x. Let's use this long division approach to help us to determine what are the other linear factors, okay? So with the long division approach, what you always want to do is to eliminate your first term. This is 2x cubed. So to eliminate that, you want to make sure you have 2x cubed under 2x cubed, okay? So to figure that out, you're going to take x, which is your first variable in your linear factor, and you're going to divide it into 2x cubed. If I divide x into 2x cubed, I'm going to get 2x squared, which you put in your quotient one time. So dividing x into 2x cubed, which is 2x squared, put that 2x squared in your quotient, and then you're going to multiply 2x squared by each term in your divisor. Alright, so when you multiply 2x squared by each term in our divisor, look at what's going to happen. 2x squared by x gives me 2x cubed. So I can put 2x cubed under itself, and 2x squared by plus 3 will give me plus 6x squared. So I can put 6x squared under 7x squared. And what I'm going to do now is to subtract, so I can eliminate my 2x cubed. And when I subtract, look at what's going to happen. 2x cubed minus 2x cubed is 0, that's gone. I'm going to say now 7x squared subtract 6x squared will give me 1x squared or x squared. And then what I'm going to do is bring down. You know, from long division, after you subtract and you get your remainder, then you must bring down. You bring down plus 3x. So let me do the same process. You see this x squared here? I want to eliminate this x squared. So how do I eliminate this x squared? I'm going to take my x in my linear divisor and I'm going to divide it into x squared. So when I divide x into x squared, I'm going to get x, and I'm going to put x in my quotient. Remember that on top there is known as a quotient, right? So remember that if you see the word quotient, you know what I mean. And now let me take x in my quotient and multiply by these two terms of the linear divisor, yeah? So I'm going to get x by x will give me x squared. So you see I got x squared under x squared, and I'm going to multiply x by plus 3, which is plus 3x. Good? And this is good, right? When I subtract these two now, look at what's going to happen. Of course, x squared minus x squared is 0. So let me put the subtraction sign in between. X squared minus x squared is 0. So we're going to get 0 here. And 3x minus 3x is 0. Very good. So it means that once you arrive at 0, it means that x plus 3 is a factor, clear, of this cubic polynomial, and the 2x squared plus x in the quotient will help you to get the remaining linear factors. So when you divide this into your polynomial, you work it out. Once you get 0 at the end of your process, then your linear factors can be easily obtained. Look how easy we're going to obtain it. We know that our dividend, 2x cubed plus 7x squared plus 3x is equal to what? Your dividend is always equal to, and when I wrote it first on the board, the dividend is always equal to the divisor multiplied by the quotient. This is how you get your linear factors, plus remainder. That's the first thing I wrote down on the board with the introduction to remainder factor term. The divisor is this x plus 3, which is one linear factor, times your quotient. Your quotient is what? 2x squared plus x, which is another linear factor. Plus, which is another factor, by the way, not linear, but another factor, plus your remainder, which is 0, which you can ignore. So these, when I multiply these two sets of factors, is going to give me back this cubic polynomial. And the thing about this second factor, what I can do, I can further factorize it. Yeah? Where I can represent my linear factors as 3 factors. Yeah? If I factorize this, so this is your answer, you can leave this as your answer, but this factor 2x squared plus x can be further factorized. You can write this as x plus 3, and let me further factorize this. This is, of course, times, x is common, take out x as a common factor, divide x into 2x squared to give you 2x, divide x into plus x to give you plus 1. And now, when you multiply these two sets of factors, you can have a nice representation of all the factors of this cubic polynomial. It's going to be, you can write x first, x plus 3 after, 2x plus 1 after. So the factors, when they ask you to determine all linear factors of this cubic polynomial, all the linear, the keyword linear factors, these are the linear factors. We can leave it like this because 2x squared plus x is not a linear factor. So what it will require you to do is further factorize this. When you further factorize it to get x into 2x plus 1, and then you multiply these two sets of factors here, you're going to get x into x plus 3, 2x plus 1, and 1, 2, 3 are linear factors. They are all linear factors. Okay? So you have taken this cubic polynomial and you have represented it as linear factors. Determine all linear factors of f of x. Everybody with thumbs up, can I see a show of thumbs? We clear how I got this? We clear how I got the linear factors as that? Using this method of long division. We clear this method of long division. Let me see a show of thumb. We clear that method of long division. Because you know many students have problems with the long division. Many students have problems with long division. So make sure you're clear on the method of long division. What it will do is to help you to get the other, to get your other linear factors. Because to do so, you have to take the divisor, you have to multiply by the quotient, add the remainder. Alright, so this is my divisor times my quotient. But then with my quotient, I can further factorize it to get 2 linear factors. And therefore, I will have 3 linear factors at the end of my representation. We clear on that? Let me see a short term. Short term. Is we clear on that? Short term? Yeah? Nice. So you want to make sure you understand that. Make sure you understand how to get linear factors. If one is not given, you have to use trial and error to get the first linear factor, then the long division approach to help you to get the remaining linear factors. Alright? So make sure we're clear on that. Alright, so alright, okay, and sometimes I ask you to compute the roots of the function. Okay, so just like when you solve a quadratic equation, when you factorize it, you get 2 sets of binomials, and then you say either you take one, put it equal to 0, you find x, and then you take the other, put it equal to 0, find x. That's what I want us to do here. Compute the roots of the function f of x. So the roots are the x values, right? It's where the any curve cuts the x-axis. And look at what the roots will be here. You're going to say for this part, after you, and this is more or less fact. What we have done here, this is a linear fact. We have factorized this cubic polynomial. We have represented it as a product of factors. We have factorized it. Good? So this is factorization here, right? Using remainder theorem. Okay? Remainder and factor theorem. So what we're going to do is we're going to basically, when they ask us to compute the roots, is really taking f of x, putting it equal to 0. F of x is this cubic polynomial here. 2x cubed plus 7x squared plus 3x is equal to 0. This cubic polynomial we factorize, we represented it as a product of linear factors. X into x plus 3, 2x plus 1 is equal to 0. And look how easy we're going to compute the what? Roots, which are all the values of x. We're going to say what? X is equal to 0. Put your first linear factor equal to 0. That's one root. The other root is what? X plus 3 is equal to 0. X is negative 3. That's another root. And then the last root is what? 2x plus 1 is equal to 0. 2x is equal to negative 1. X is equal to negative a half. So that's how you compute your roots. So find the roots after factorizing the cubic polynomial. Alright? So this part pretty straightforward to get those roots. So if you see that in the exam on Tuesday, you know what is required of you. Alright? Alright, so let's move on now to some surds, indices, and logarithms. Let's look at that. Yeah? Right, so I know students, often have little challenges with the logs in particular, right? Of course, with a surd, you know what's a surd? A surd is, just to keep it simple, it's a non-perfect square under the root symbol, yeah, otherwise known as a radical. So if you have here, 2 is a non-perfect square, 3 is a non-perfect square, 5, a perfect square will be if you have 4. 4 can be expressed as the product of the same two factors. 9, 16, all those are perfect squares, right? But a non-perfect square will be like 2, 3, 5, 15, 45, all those are non-perfect squares. So if you put a non-perfect square under a root symbol, otherwise known as a radical, what we have here is a surd. Good? If you put a perfect square under a square root symbol, that is not a surd. The square root of 4 is 2. The square root of 9 is what? 3. So these are surds here. Alright? So they want us to, let's look at this first question. This is from June 2022. Show that the expression we have the square root of 25 all over the square root of 45 is the same as the square root of 5 over 3. Good? When you look at the denominator, you see this here? The square root of 45 is a surd. That's a surd one time. The square root of 25 is not a surd. You can find the square root of 25 to give you 5, you know that off the bat. But the square root of 45 is not a surd. Yeah? Now, the thing with surds, you can always simplify a surd. You can always simplify it. So, the square root of 45, we can simplify that surd. We know it's a surd and we can simplify it. We can write this as, well, let me put the square root of 25 as 5 one time. And let's simplify the square root of 45. To simplify a surd, you want to represent the number under the root symbol, which is 45, as a product of two factors, where one factor is a perfect square. Remember, just showed it was a perfect square, right? 4, 9, 1, 16, 25, all those are perfect squares. So you want to represent this 45 as a product of two factors, where one of them is a perfect square. So we can easily think of what? 9 by 5. 9 by 5 is 45, where 9 is a what? 9 is a perfect square. Yeah? 9 is a perfect square. And look at how we're going to simplify this further now. So this is where you have to know your rules of surds. So there's the rule of multiplication of surds. So if I have this, so with the rule of multiplication of surds, you can write this as the square root of A by the square root of B. You can separate it like that. So the square root of 9 by 5 can be written as 5 all over the square root of 9 by the square root of 5. Yeah? And we know that the square root of 9 is the same as what? This is now, of course, a perfect square. The square root of 9 is 3. This becomes 5 all over 3 root 5. Good? But remember what the question asks us. We're not finished yet, because they ask us to show that the expression is the same as the square root of 5 over 3. We have to show that this is the same as the square root of 5 over 3. What I've done here is just to simplify this further. Let's just simplify it. And now I'm going to use this simplified representation to show it's the same as that. So how am I going to show it's the same as that? Now in surds, or with surds, you never work with a surd in your denominator. You say I have a surd in the denominator here, the square root of 5. You never work with a surd in the denominator. So there's something you can do to remove the surd from the denominator, and it's called rationalization. Yeah? Let me see if we know about rationalization. Let me see a show of thumbs. You know about rationalization? Let me see a show of thumbs. So make sure you know this for surds, because it's highly possible they could bring a question like this in the exam on Tuesday, where you have to rationalize to remove that surd from the denominator. Yeah, short term, good, nice. So, to remove the surd from the denominator, to rationalize, I am going to multiply this fraction by another fraction whose numerator and denominator, so I'm multiplying this fraction by another fraction whose numerator and denominator will be the denominator of my first fraction. So the denominator of my first fraction is 3 root 5. So I'm going to put that in the numerator of this fraction, and the same denominator, 3 root 5, will be placed in the denominator of that fraction. So you're placing what you see in the denominator of your first fraction in both numerator and denominator of the fraction that you are multiplying this first by. Okay? So let us now multiply both numerator and denominator, and let's see if it's going to simplify to what we have there. Let's see. So the first we did was simplify, and now we rationalize it. So this becomes what? 5 by 3 root 5 becomes 15 root 5. 15, the square root of 5, all over 3 by 3 is 9, and the square root of 5 by the square root of 5 is the same as 5. If you have the square root of 5 by the square root of 5, rule of surds, 5 by 5 is 25, and the square root of 25 will give 5, right? So 3 by 3 is 9 times the square root of 5 by the square root of 5 is the square root of 25, which gives 5. And therefore, what you're going to get here? You're going to get here 15, the square root of 5 all over 45. And let's simplify it. I can say now 15 into 15 is 1, and 15 into 45 will give me 3. So I'm going to get the square root of 5 over 3. Alright? And when they ask you to show something in AddMath or math, you always write at the end, hence shown. So we have shown that this expression given can be simplified to what we have there by, again, simplifying the surd in the denominator. Of course, expressing it as a product of two factors, where one is a perfect square. And when we do so, after we simplify it, there's still a surd in the denominator, and therefore we have to what? Rationalize. We're going to multiply that by a new fraction whose numerator and denominator will be the denominator of your first fraction. Yeah? So this will be 3 the square root of 5 in your numerator, 3 the square root of 5 in your denominator, and then you multiply numerator by numerator, denominator by denominator. We simplify to give us the final result. Alright? So just making sure we're clear. Can I see that short term? We clear on that? Let me see if we clear on that. Everybody, we clear on that? So make sure you understand surds. Okay? Clear on that, everybody? Alright, nice. So let's look at now. Alright, so let's look at another surd question. If they brought something like this. Right, so just in case, if they brought something like this, if they have, they wanted to simplify something like that, right? That is also, clearly we have a surd in the denominator. You never work with a surd in the denominator, alright? Never. So what you want to do is to simplify where that surd in the denominator can be removed. So to remove that surd from the denominator, we're doing the same thing. We're going to rationalize. meaning you're going to multiply this fraction by another fraction whose numerator and denominator will be, and this time you have to be very careful. We can't put the same thing we see here. Okay? If we had one term, then yes, we can put that one term in the numerator and denominator. This time you have two terms, 4 plus the square root of 7. So what you're going to put in both numerator and denominator is something called the conjugate. You know, ever heard about the conjugate? Conjugate? Yeah, conjugate. So if you have 4 plus the square root of 7, the conjugate of that is just a change in sign. This is the conjugate. If this is this, that's the conjugate of it. You just change the sign to 4 minus square root of 7. You ever heard of the conjugate? Right, nice. So what you do is you put the conjugate in the numerator and denominator, not the 4 plus the square root of 7. It's the conjugate of it. Alright? And what you're going to do now to help you to remove the surd from the denominator is to multiply 6 by the numerator, and you're going to multiply 4 plus the square root of 7 by 4 minus the square root of 7. Good? And let's work it out. We're going to get what? This becomes 6 by 4 is 24 minus 6 by the square root of 7 is 6 the square root of 7. Over. This will be 4 by 4, which is 16. 4 by negative the square root of 7 is negative 4. The square root of 7. The square root of 7 by 4 will be positive 4. The square root of 7. And positive 7 by negative 7 will be negative. That's negative the square root of 49, which is 7. Yeah? So therefore this becomes what? 24 minus 6 the square root of 7 all over negative 4 the square root of 7 plus 4 the square root of 7 are like surds. Those are like surds, and therefore we can simplify by simply cancelling those two. That becomes 0, and you're going to have 16 minus 7. Yeah? And 7 from 16 will give us 9. Alright? And that's removing your surd from the denominator. Alright? So, simple. Make sure you understand that. It's possible you can see it in your exam Tuesday. So, you want to make sure you're clear on it. Alright? So, this here is a question on surds. Let's look at now some logarithms. Let's look at some questions on logs, right? Yeah? So, I'll start off with, alright, let's start off with this one here. Alright, so let's do just a few questions with the logs. Make sure you know we clear on the logarithms, and then we look at some exponential equations, making sure you know we understand our indices. And then we move on to some quadratics, okay? Now, so with logarithms, you want to make sure first you understand all your laws of logarithms. You have to know all your laws. So your laws of logarithms are important. You know, there are some key laws that are always used. So let's make sure you remember the laws. The laws right? Now, well, first of all, before getting into the laws, make sure that you know how to, when it comes to logarithms, make sure you know how to move from the exponential form to the logarithmic form and vice versa. So, for example, if I have 8 is equal to 2 to the power of 3, that is exponential form. And if I have to convert that into logarithmic form, what I'm going to do is put log in front of my 8, 2 here, which is the base of the exponential form, and exponential is the same as index, right? Base and power. 2, which is the base of your exponential or index form, becomes the base of your logarithmic form, and that will be equal to 3. Yeah? So 8, you put log in front of it, 2 the base becomes the base of the logarithmic. So just remember this is base, so that becomes the base, and 3 the index will be your result. And you can also do the vice versa. You can move from here back to here. So just simply take the base 2, put it as the base of 3, and drop the log function. So this becomes 2 to the power of 3, drop the log function, and that is equal to what? 8. So you can move from exponential form to logarithmic form. Alright? And there are some other things you need to know in terms of, if you have, for example, 100 is equal to 10 squared. Alright? 100, if I have to convert that from exponential to logarithmic form, is going to be log of 100. The base 10 becomes the base of the logarithmic function. So remember, this is the base, so that becomes the base of log, and that will be equal to what? 2. Alright? But there's something I want you to also recognize. Sometimes with logs, instead of seeing log all the time, when it's a base of 10, anytime it's a base of 10, or if not, if 10 is not there, if you see log of 100, 10 is understood. If 10 is not there, no base is there, 10 is understood. Alright? So let me put back the 10. So if there's no base, 10 is understood, right? So you can write this, when the base is 10, the log notation can be represented as LG. LG, which is also known as a common logarithm. Yes, if you see LG, there are 3 log notations. You see LOG, you see LG. So make sure if you see LG in the exam, don't get confused. It simply means that your base is what? 10. And if you put log of 100 in your calculator, if you put log of 100 now, take your calculator and find log of 100. What you're going to see? 2. Yeah? You're going to see where the answer is 2. So once the base is 10, you can simply punch it into the calculator and get a result. If the base is not 10, like in this case 2, you cannot just easily put it into the calculator and get a result. That can't happen. The only way you can get a result is once the base is 10. So moving from exponential to logarithmic form, if you see the base is 10, the log notation we use is LG, and that's known as a common logarithm, right? And you also have, if you have, for example, if you have, say, e to the power of 1, and e to the power of 1 is the same as, let me get the exact representation here. E to the power of 1 is 2.718. Then, now this here is exponential form. E is my base, 1 is my power, is equal to 2.718. If I have to convert this into logarithmic form, I'm going to put log of this 2.718. Remember, E is the what? E is the base. So that becomes the base of your log notation or log function. And that will be equal to the index of power, which is 1. And remember, the vice versa can always be done for you to move from logarithmic back to exponential. And it's good to know how to move from exponential, what we're doing here, to logarithmic, and the vice versa, from logarithmic back to exponential. But there's something you need to know, another log notation you need to know. If log is raised to, is to a base of e, what we're going to use is ln. Right? Ln of 2.718 will give us 1. So when you have a base of e, just keep in mind the log notation we're using is a ln. Okay? And that is known as the natural logarithms. You have the natural logarithm. Alright, so there's some things we need to know when you treat them with logs here. Make sure you know if you see LG in the exam, don't get lost if you see LG, the base is 10. If you see LN, know the base is E, don't get lost. If the base is not 10 or E, for example, 2, 3, 4, 5, and so on, note you're going to normally use LOG. Alright? So let's look at the laws, some of the laws, and then we're going to look at apply to this question here. So let's look at some of the laws. So the laws. So making sure we know how to move from exponential to logarithmic and vice versa. So what are the laws of logarithms? Right? So the laws of logarithms is simply this. If you have log of a to base a, that is always equal to 1. So for example, if you have log of 5 to base 5, that is equal to 1. Good? Always remember, log of 1 to base a, that is equal to 0. So for example, if you have log of 1 to base 2, that is 0. Yeah? Remember an important law which is called the power law. So the power law is if you have log of a to the power of b to base c. Very important law of logarithms. Yeah? That law is the power law. Once you have a power, you'll take the power, put it in front of the log function. And a to base c stays as is. Yeah? And the vice versa can be done. You can move from here back to here. So the vice versa can be done. So that's the power law. You also have the product law. Right? Remember the product law, because we're going to see where the product law, both product and power law will come into play with that question. So the product law, if you have log of a multiplied by b to base c, product a multiplied by b, and please note, you see this a here, c is your base, but a here you call it the argument. You call it the argument, right? So when you see this, whatever number is represented here or whatever variable is represented here, it's known as the argument. So a multiplied by b is your argument, and that shows the product, and we can represent this as a log of a to base c plus log of b to base c. Right, as a product law, we also have another important law, which is the quotient law. I mean, what quotient means to divide, right? So if you have log of a over b to base c, you can write that as a log of a to base c minus log of b to base c. Okay? And also remember the vice versa can occur. Vice versa. You can move from here, addition, back to the product, subtraction, back to the quotient, from what we have here, back to the power. Yeah? So, let's look at this question here. Log of x plus 1 plus log of x minus 1 is equal to 2 log x plus 2. They want us to solve that equation. Of course, if you have to solve an equation, you're solving for the unknown x. Good? So we're going to solve that equation. Now, in solving equations in logarithmic form, what you always try to do, you always try to get single log functions on either side of the equal sign of the same base. Meaning you want one log function on the left, one log function on the right. So you want something looking like this. One log function on the left and one log function on the right of the equal sign. And once you get to that, then what you can easily do now is equate the arguments. You can put the two arguments equal to each other and go and solve for what is required. So with logs, when you have an equation in logarithmic form, you want to get to what? single log functions on either side of the equal sign. One log function on the left, one log function on the right. Now, when we look at this equation right now, this log function, the base is 10. You're not seeing 10 there, right? But it's understood. 10 is understood there. So the base is 10. And for us to solve that, we have two log functions on the left and one log function on the right. Let's try to get one log function on the left, one log function on the right. So how are we going to do that? With what is on the left, to get one log function, we are applying the rules we know. What rule we know? We see where we have addition. We have addition here, and that can be converted back to your what? To the product. So we can write this as a log of x plus 1 multiplied by x minus 1. Keeping in mind a base of 10 is understood here. Good? So now we've moved from two log functions separated by an addition sign, of course, and we've moved it to one log function. Is equal to, we have one log function on the right, but 2 log x plus 2. What we can apply here now is the very important law known as the power law. So you have your b log a to base c. This b will come as the power of a. This 2 will become the power of x plus 2. So we're going to write this as a log of x plus 2 raised to the power of 2. So what we have here are two single log functions now on either side of the equal sign of the same base. And all you have to do now, once you achieve that, single log functions on either side, all you have to do now is just equate the arguments. See these two? Those are arguments. Good? Remember, base of 10 is understood here, even though it's not seen. The base is 10 is understood. Yeah? So all you're going to do is put the two arguments equal to each other. That will be what? X plus 1, x minus 1 is equal to x plus 2 all squared. Yeah? And what we're going to have here is an equation, look like a quadratic equation. Let's work it out and see what we're going to get. Let's expand it. X by x, x by negative 1, 1 by x, 1 by negative 1. X by x gives x squared. X by negative 1 gives negative x. Positive 1 by x gives positive x. Positive 1 by negative 1 gives negative 1. Let me expand what I have on the right. That's x plus 2 by x plus 2. So we're expanding that. So we're going to get what? Of course, let me simplify this side a little more. This becomes negative x plus x will be 0. I have x squared minus 1 is equal to, let me expand what I have on the right. I'm going to get x squared plus 2x plus 2x plus 4. And therefore, I'm going to get what? X squared minus 1 is equal to x squared plus 4x plus 4. Good? And let me bring everything over on the right onto the left-hand side. Right? Let me bring everything on the right to the left-hand side equal to 0. So let's see what we're going to get. This becomes x squared. Positive x squared comes across as negative x squared. You have negative 1. Positive 4 comes across as negative 4. You have positive 4x comes across as negative 4x is equal to 0. Alright, let's simplify what we have on the, I thought it would have worked out a quadratic, and clearly it's not going to work out a quadratic. So look what's going to happen. X squared minus x squared will be 0, that's gone. Negative 1 minus 4 is negative 5. Minus 4x is equal to 0. And now let's make x a subject. So we're going to what? Take negative 5, put it on the right. And then we can comfortably divide both sides by negative 4. So we're going to get what? Negative 4x divided by negative 4. X will be equal to negative 1.25. That is us solving that equation in logarithmic form. Yeah? Solving that equation in logarithmic form. Yeah? So by first ensuring we have single log functions on either side of the equal sign, and then we equate the arguments, creating an equation and hence solving for the unknown. Yeah? All right, let me see by short term. I know it was a lot, but let me see by short term. Are we clear what I did there? Make sure you know how to solve that log equation. Getting single log functions on either side and using your rules. Using those rules. Short term, we good? Yeah? So I know it's a lot to take in. So again, if you have to go and get some water, wash your face, make sure you do so. Yeah? There's a lot to take in. Yeah? Alright. And don't forget to share, like, subscribe, tell all your friends so they can be a part of what's going on. Okay? Alright. So let's look at another question involving logs. All right, we can try this one here. Let's look at this one. Now, of course, we have two parts here. The first part is known as an exponential equation. We're going to be looking at, one or two exponential equations. So we'll come back to this one here, which is an exponential equation. So you have logarithmic equations, you have exponential equations. So let's look at this logarithmic equation here, right? So this will be log, and let me just write it over just in case it's a bit blurry. This is log x plus 2 to the base 3 plus log x minus 1 to the base 3 is equal to log 6x minus 8 to the base 3. Now what you think is the first thing we have to do? We have single log functions on either side of the equal sign. What do you think we have to do to get a single log function on the left? What law we have to use? You tell me what law we have to use to get a single log function on the left. Tell me what law we have to use. Let me see if you can tell me. So this representation on the left here. What law? To get a single log function. How many laws written on the board here? Let me see if you can tell me. Anybody? What law? Good. The product law. Nice. Thumbs up. So let's get a single log function on the left. So this becomes what? Log x plus 2 x minus 1 to the base 3 is equal to log 6x minus 8 to the base 3. So now we have a single log function on the left, single log function on the right. And once we achieve that, what we're going to do now is equate the arguments. You're going to put these two equal to each other. Yeah? So you're just going to put them equal to each other and drop that log 3. So this becomes what? X plus 2, x minus 1 is equal to 6x minus 8. Then, and what we're going to do here now is solve that equation. So let's expand what we have on the left. You're going to get x by x, which is x squared. X by negative 1 is negative x. Positive 2 by x is positive 2x. And positive 2 by negative 1 is negative 2. And that is equal to 6x minus 8. Good? So let's simplify. So you see a quadratic equation developing here. So you're going to get x squared plus x minus 2 is equal to 6x minus 8. And let me bring everything over to the left-hand side of the equal sign. Let's erase everything I have here. So when I get x squared plus x minus 6x minus 2, negative 8 comes across as plus 8 is equal to 0. And you're going to get x squared minus 5x plus 6 is equal to 0. And then let's factorize what we have on the left. That is a quadratic expression, which we should all know how to factorize. So I'm going to multiply a by c, 1 by 6, which will give me 6. And I want two factors of 6 that will help me to get this middle term, negative 5x. And the two factors of 6 I can use are 3 by 2 and a plus sign, of course, 3x, 2x. A plus sign tells me the signs must be the same here. This minus sign tells me both are negative. So I know it's negative 3x minus 2x. I'm going to replace negative 5x with, this becomes x squared minus 3x minus 2x plus 6 is equal to 0. I pair off. What is common to my first pair? X. I'm going to get x minus 3. Let me factorize my second pair. I bring down the negative sign that controls the first term of the second pair. What else is common? 2. So negative 2 into negative 2x is x. Negative 2 into plus 6 is negative 3. Once I arrive at the same thing in brackets, we know we're on the right track. So this becomes x minus 3. X minus 2 is equal to 0 to further factorize. And we can say here now either x minus 3 is equal to 0, x is 3, or x minus 2 is equal to 0, x is equal to positive 2. And that's us solving that equation in logarithmic form. You see that? So getting single log functions, make sure you're applying your laws and you equate the arguments. Alright? Then I see short term. We clear on that? Everybody, we good with that? We good with that? Short terms. Oh, I got the two values of x there. Right? Everybody good? Nice. Just. Alright, nice. Okay, so let's look at now with logarithms. Right, now we can see something like this. Everybody know that that's a common one, right? That's a common one. We have to show that x is equal to that. And again, applying, your knowledge of logarithms and laws too, right? And laws too. What I'll do after, I will look at one or two exponential. Well, in fact, no, before I do the exponential, I'll just show you all, you have conversion to linear. So sometimes they'll give you a non-linear function and ask you to convert it into a linear function in the form y equal to mx plus c. So let's make sure we can take a non-linear and convert it into a linear form, alright? So and then we look at one or two exponential equations, and then we get into quadratics after that. Alright? Now, we have this here. Given 5 to the power of 3x minus 2 is equal to 7 to the power of x plus 2. Alright? And they ask us to show x is equal to what we have here. Again, we're going to apply our laws of logarithms to help us to do so. Now, this here presently is an equation in exponential form. Because exponential form means you must have a base and power. And the unknown x is represented in the power. So it becomes an exponential or an equation in index form. That is what that is. But we're going to see when we do one or two exponential equations that to solve an exponential equation, just like with the logs, you try to get a single log function on the left with the same base, single log function on the right with the same base, and then you equate the arguments. Same thing with an simple exponential equation. You try to get one term on the left with the same base. So for example, this is a simple exponential. 4 to the power of 2x is equal to, say, 16. That's a simple exponential equation. You know, if you have to solve this, you want to get single terms on either side of the equal sign with the same base. So this is 4 to the power of 2x. 16 is the same as 4 squared. Single terms on either side of the same base. And what you can do now is just put the powers equal to solve for x. So once you get a single term on the left of the same base as that of the right, all you do is equate the powers, put them equal and solve for x. This is a simple logarithmic equation. Alright? So if we were to, and this is also a simple logarithmic equation, but, well, this is a logarithmic equation, but look at what's happening here. There's no way I can get a common base to 5 and 7. I can get a common base of 4 and 16, yeah, which will allow me to then equate the powers. But there's no way I can get a common base to 5 and 7. So therefore, I cannot proceed to try to equate my powers. That can't happen just like that. So what I have to do now, when that cannot happen, we introduce logs. So for example, if you have 3 to the power of x is equal to 7, you can't get the base as the same on either side, so you have to introduce logs. Find the log of both sides. So that's the first thing you do. You find the log of both sides if you can't get the same base on either side. Single, but equal base on either side. So the same thing is happening here. I can't get a single and equal base on either side. So I'm going to introduce a log. So I'm going to find the log of both sides. So this becomes a log of 5 to the power of 3x minus 2 is equal to log of 7 to the power of x plus 2. Right? So I'm finding the log of both sides. And now, what am I going to do? I'm going to apply the law that I'm familiar with. That law, it is the power law. So I'm going to take this power, 3x minus 2, and I'm going to put it in front of the log notation. So this becomes 3x minus 2, and you make sure you put the 3x minus 2 in brackets. Log 5 is equal to, take the x plus 2, put it in front. You should put the x plus 2 in brackets, log 7. Alright? Now what can happen here, because log 5 and log 7 we can work out, because this is the base of 10, you can work this out on the calculator. You can get a decimal number for this. You can get a decimal number for that, yeah? But remember, they don't want us to convert it into any decimal number because they want us to show that x is equal to this. Okay? So we have to make sure we maintain the log 7 with log 5. Now, what we can do here, because this can be converted into decimal numbers, we can easily remove the brackets. So we can remove the brackets. So this will be what? 3x log 5. So I can remove the brackets here because this can be converted into a number, decimal number. And if it was a number, you could have easily removed the brackets. This will be log 5 by negative 2 becomes negative 2 log 5. I can do the same here. This can be converted into a number. Log of 7 I can work out on my calculator and get a decimal number, which I can then multiply by each, but I'm not going to convert it. I'm going to leave it as log 7. This is x log 7 plus 2 log 7. Okay? But then our aim is to get x as the subject. You want x by itself. So it means that all terms involving x, you want to put on one side of the equal sign. Put all terms involving x on one side of the equal sign. So I'm seeing a term involving x here, and I'm seeing another term involving x here. So we bring all terms involving x on the left. This is 3x log 5. Positive x log 7 comes across as negative x log 7. And we want everything else that doesn't involve x, put it on the other side. So you're going to have your what? You're going to have 2 log 7 and negative 2 log 5 comes across as positive 2 log 5. Okay? So we get to that point, all right, where we have all the terms with x on one side, anything else that doesn't involve x on the other. So what are we going to do here? So to get x as a subject on the left of this equal sign, to get x by itself, we have to carry out a bit of factorization. So you're going to pull out x as a common factor. You have to factorize here so you can get that x by itself. When you pull out x as a common factor, x into 3x log 5, my x divided into x is 1, which will leave me with 3 log 5. And let me divide x into negative x log 7. My x into negative x gives me negative 1 log 7, or negative log 7. Yeah? Same thing. Look at what we want to achieve. We want to achieve this 2 log 5 plus log 7, alright? Yeah? 2 and in brackets log 5 plus log 7. Which we're going to get too shortly because we're near to that, right? So I'm going to, on my left, looking at what I want to achieve, 2 log 5 plus log 7. I'm seeing 2 log 7 plus log 5. You can put a log 5 in front, 2 log 5 in front, and 2 log 7 after if you want to interchange them. So it will look exactly like that, no problem. If you want it to look exactly like that, no problem. If you had it as is, no problem as well. It doesn't matter the order. And what I can do here as well is factorize. So I'm going to get x 3 log 5 minus log 7. I'm also going to factorize here, pull out 2. I'm going to get log 5 plus log 7. Yeah? So now I'm seeing where this is clear to me. And on the right now, I can make x the subject by removing that in brackets 3 log 5 minus log 7. Yeah? So the opposite of multiplication is division. So x will be equal to 2 in brackets log 5 plus log 7 over 3 log 5 minus log 7. But we just have one more thing to do to get it exactly looking like this. One more thing you need to do. And this is where your power law will come into play. See, I have this 3 in front of this log 5 here? Yeah? We're going to take that 3 and put it as a power of 5. Yeah? To get exactly what we have on the right hand side of that equal sign. So this becomes what? 2 log 5 plus log 7. Apply the power law. This becomes log 5 to the power 3 minus log 7. And therefore, you're going to get what? 2. Let me put this in brackets. You're going to get it 2 log 5 plus log 7 over 5 cubed is 125. Log 125 minus log 7. And we have shown that x is equal to that. And when you show something in AddMath or math, you put hence shown. Alright? So we have shown that x is equal to what we have there by moving from an equation in exponential form, finding the log of both sides, and simplifying to get what we have as our final representation. Short term, we good at that? We good? Everybody? Short term? Are you good with that? Right, nice. All right. So let's look at a simple exponential equation. Then we look at a complex one. Let's do a quick conversion to linear law, converted in the form y equal to mx plus c, and then we move to quadratics. All right. So all right, so this is a simple exponential equation. 16 to the power of x plus 2 is equal to a quarter. Simple exponential equation. So we want to solve that. So to solve that, what we want to do is obviously try to get single terms on either side of the equal sign of the same base. Right? And we can do so because you can convert 16 to a base of 4. 16 is the same as what? 4 squared to the power of x plus 2. And a quarter can be expressed as, from your laws of indices, you have to know your laws of indices. Remember the law of the negative index. This 4 will move from the denominator to the numerator, and positive 1 becomes negative 1. So you're moving from the negative index to the positive index, to the negative index. And if you look on the left, we've seen a single term of a base 4. On the right, we've seen a single term of the base 4. And what we can do here now is apply the law of power to a power. I take the power outside and I multiply by the power within. I'm going to get 4. 2 times x plus 2 is equal to 4 to the power of negative 1. And what can happen here now? I can say for an equal base, and this is the thing when you're solving equations, simple equations in exponential form. Once you arrive at a single term of the same base on both left and right of the equal sign, what you can do now is equate the powers. So you can put the powers equal to each other. So for an equal base, we equate the powers. So when we equate the powers, what are we going to get? 2 into x plus 2 is equal to negative 1. 2x plus 4 is equal to negative 1. 2x is equal to negative 1 subtract 4. 2x is equal to negative 5. X is negative 5 over 2. Straightforward, simple. Yeah? So we found for x. Simple. See that? That's a simple exponential equation. Everybody good with that? Good with that? Job done? Yeah? We good with that? Right, nice. But let's look at a more complex exponential equation. Right, let's look at something like this. Good? A more complex, and this is something you have to make sure you look out for, because it's possible you can see something like this in your exam on Tuesday. Let's make sure we can trick with solving an exponential equation like that one. Okay? Now, so with an exponential equation like that one, right, so to solve that one is not, easy like the one we did just now there, where it was easy for you to get single log functions, single terms of the same base on either side of the equal sign. It was not as easy as that one. So it was easy for us to get 4, a base of 4 on the left, a base of 4 on the right, and then equate the powers. No matter what we try to do here, we can't. Alright? You know from your laws of indices, there's no law of subtraction, there's no law of addition. Alright? There's law of multiplication, division, zero index, negative index, fractional index, those laws you know. There's no law of addition nor subtraction. So there's no way of us trying to get single terms of the same base on either side. You cannot also multiply, so let's make that mistake, 5 by 2 to get 10. You cannot multiply 5 by 2 here to get 10. So no matter what you try to do, there's no way you can get single terms. And look, this is a base of 2, that's a base of 3. This is 5. No way you can get a single term of the same base on either side. No matter what you try to do here. So how are we going to solve this equation? How? Right? So to solve this equation, we're going to use our laws of indices. So law of indices or laws of indices. So laws of indices will come into play. Also, a method of substitution will come into play. And we have something called the hidden quadratic equation will come into play. So three things will come into play here. Your laws of indices will come into play, a method of substitution will come into play, and the hidden quadratic equation will come into play to help us to solve this equation, this exponential equation. So this is an exponential. And why exponential? The unknown is represented as a power, okay? So we're going to treat with this. To treat with this is what we're going to do. We're seeing 2 to the power of x here, right? So what you try to do, you try to get as many 2 to the power of x as possible in the equation. I've seen one here, but where am I seeing another? And there's a reason for us trying to identify how many 2 to the power of x we can. So I'm seeing one here. So where else can I find one? You see this 2 to the power of 2x plus 1? I can find one here. But how, right? This is what you're going to do. This is where your laws of indices will come into play. You're going to write this as 2 to the power of 2x multiplied by 2 to the power of 1. And you know the law of multiplication of indices. Once I have the same base, I keep the base 2. And what I do with the powers? Add the powers. So this can be expressed as this, and vice versa. I can move from here back to here. So what I've done is to take this, using my law of multiplication of indices, and I've represented it as 2x, 2 to the power of 2x by 2 to the power of 1, plus 5 open brackets, 2 to the power of x minus 3 is equal to 0. I'm still not seeing a clear 2 to the power of x. So how can I see a clear 2 to the power of x? This 2 to the power of 2x can be rewritten as 2 to the power of x squared. That's 2 to the power of 2x. It's the same as 2 to the power of x squared. Multiplied by 2 plus 5 times 2 to the power of x minus 3 is equal to 0. So I have recognized how many 2 to the power of x now in my equation. 2 of them. Yeah? Now this equation you're seeing here is a quadratic equation. You may not see it. But you know what will help us to see it clear? You know what will help us to see it clear? We are going to now use this method or approach of substitution to help you to see it clear now. And then we're going to get the hidden quadratic. We're going to pull out our quadratic from that, which in turn will help us to find what is required. So this here, this equation, now that we have recognized clear 2 to the power of x, there are no more we can get from it. We're going to say let this 2 to the power of x be some letter. Yeah, from A to Z, you pick one, right? So let it be u. Let's put u. So I'm going to replace this 2 to the power of x with u. U squared times 2 plus 5 times u minus 3 is equal to 0. Yeah? Which will then simplify to become u squared by 2 is the same as what? 2u squared plus 5u minus 3 is equal to 0. Isn't this clear to us now? Isn't this a clear equation, which is a what? Quadratic equation? Yeah? What I did here is to use my laws of indices to pull out as many 2 to the power of x. I'm seeing one here. I can get one from this. So I use my laws of indices to separate it. Use my laws of indices to convert 2 to the power of 2x as 2 to the power of x all squared. X by 2 will give you the same 2x. Good? I recognize how many of them? 2 of them, 2 to the power of x. And this is where I'm now introducing my method of substitution. So I let 2 to the power of x be any letter of the alphabet. You pick one. I just went with u. And I replace 2 to the power of x with u. So I get u squared times 2 plus 5 times u minus 3 is equal to 0, which becomes a quadratic equation now. So let's solve that quadratic equation to get values of u. And then, remember, this equation is not finding u. We have to solve x. That's the unknown in the equation, x. But we're using this process to help us to find it. So let's solve this quadratic. I'm going to multiply 2 by negative 3, which is negative 6. And I want 2 factors of negative 6 that can help me to get this middle term plus 5x. The 2 factors of negative 6 I'm going to use, I can use positive 6 and negative 1. 6u, sorry, minus 1u or minus u will give me 5u. And a minus sign in front, you can check your signs too. A minus sign in front of the constant tells you that these signs must be different. And this plus sign in front of the 5 will tell you the larger term is controlled by a plus. These are some rules of signs of the quadratic which are important to know to help you. So now that my middle term has been achieved, let me now rewrite this as what? 2u squared plus 6u minus 3 is equal to 0. Let me pay off now. When I pay off, I can take what as a common factor 2u. So 2u into 2u squared gives me u, and 2u into plus 6u gives me plus 3. Let me factorize the second pair. The sign controlling the first term of the second pair I bring down automatically. There's nothing common to u and negative 3. So 1 is understood always after an addition or subtraction sign. So negative 1 becomes my highest common factor, which I'm going to divide now into each term. Negative 1 into negative u gives me u, and negative 1 into negative 3 gives me plus 3 is equal to 0. And what I can do here now is further factorize. I pull out u plus 3, and 2u minus 1 is equal to 0. Alright? And what I'm going to get here now are two values of u. Alright? So what I'm going to do, let me just pull down this PowerPoint just to get some space. I'm going to get two values of u. I'm going to say either u plus 3 is equal to 0, u is negative 3, or 2u minus 1 is equal to 0, 2u is equal to 1, u is equal to a half. But remember, this question not solving for u. U was used to help you to recognize or pull out the hidden quadratic. That quadratic that was hiding inside there, you use that variable u to help you to pull it out. Alright? And you got these two values of u, but the objective of this question is to find x. So how about bringing back x into the mix? This is what you're going to do. U is equal to 2 to the power of x. Yeah, so let's bring it back into the mix now. So therefore, u equal to minus 3, I'm replacing u with what? 2 to the power of x is equal to negative 3. Yes, I'll bring it back in. So we put back the 2 to the power of x in place of the u, because u is equal to that. And now let me solve for x. Now, this is a simple equation in exponential form. There's no way I can get a base of 2 on either side of the equal sign. And even if I use the logs, finding the log of both sides, I cannot find the log of negative 3. Log of negative 3 is undefined. If you put that in a calculator, you're going to see error. Undefined. So, for u equal to negative 3, when you replace that u with 2 to the power of x, we're not going to get a value for x. So, we're going to put no solution. As opposed to now, let's take u to the half. If I replace u in u equal to a half, if I replace u with 2 to the power of x is equal to a half, that is also a simple equation where I can now solve for x. A half can be written as what? 2 to the power of negative 1. Yeah? From your laws of indices. You have to know your indices, right? Your laws. Move that 2 from the denominator to the numerator and change the sign. The power from positive 1 to negative 1. And now, simple equation, simple exponential equation. Once you have the same base on either side, you equate the powers, and therefore x is equal to negative 1. And that's your answer for this question. Alright? So it is a question you want to look out for just in case you see it. Sometimes I bring it in section 1, right? It is an exponential equation, more complex exponential equation that requires you to use your laws of indices, a method of substitution, pulling out what you call the hidden quadratic hiding inside there. Pull it out, solve the quadratic, and then bring back in what you replace the that variable, that 2 to the power of x in this case, right? You bring it back into the question and solve for x. Alright? Are we clear what I did there? We clear this one? Short term? It's a very important question. Clear on that one? Okay, right. So let's now, we're just looking at one more thing with logs, and that is if you have conversion to linear, we're moving on to quadratics, right? Now, if you have here, right, so it's known as conversion to linear or linear law, right? And if you have something like this. Right, let's look at this one here. So it's good to know how to, when you're treating with logs, because it's possible you can see this in the early part of the paper. Given V and T, or sorry, an equation relating V and T is given by V is equal to Ka to the power of T. Now that's a nonlinear equation, right? Where K and A are constants. Use logarithms to derive an equation of the form y equal to mx plus c that can be used to find the values of K and A. Okay? So they want us to take this nonlinear form and convert it into a linear form, into this form. Alright? So we're going to convert it into that form. So to convert it into that form, this is where we're going to introduce the logs. Logs, right? So we are going to find the log of both sides. So we find the log of both sides. Right? So this becomes what? This becomes log V is equal to log Ka to the power of T. You find the log of both sides. Even if you want to use LG, no problem, because it's the base of 10, right? And look at what we're going to do now. We are going to, on the right, we have K multiplied by A to the power of T. This is K multiplied by A to the power of T. So you know what law will come into play now? Your product law. So this becomes log V is equal to log K, and you know for your product law, it will of course be expressed as addition of log K plus log A to the power of T. Alright? So the addition of two log functions. Good? And now, you know what else comes into play here? The power law. Look at the power law here. Log V is equal to log K plus T log A. So you take this T and put it in front of the log notation, so you get T log A. And you see this here, this is in the form y equal to mx plus c, you know. And normally when they ask you, use logarithms to derive an equation of the form y equal to mx plus c that can be used to find the values of K and A. Normally when they ask you to find those values, one will represent the gradient and the other will represent the y-intercept. Well, because with a linear equation, this is what you're looking at. So you have the gradient and you have the y-intercept, which is c. So what will represent our gradient? This is of course your y-axis, x-axis. What will represent the gradient here? The gradient will be represented by, because they want us to find K and A, one of those variables will represent the gradient, one will represent the y-intercept. So we have here y, log V represents y, log K will represent C, that will represent your y-intercept, and plus mx. Because they want us to find K and A, normally the y-intercept will be one of the variables you have to find. So log C will be our y-intercept. And you see this T log A, because they want us to find A, we're going to allow the gradient M to be log A. and we're going to allow t to be x. So what you have here is log v, which is your y, is equal to log a, which is the gradient m. X, of course, will be t, and log k will be the y-intercept. Reason why I've recognized a and k as m and c, log a and k as log k as m and c, because what they often ask you to find with questions where you're dealing with conversion to linear, one often is the y-intercept and the other is the gradient. So log k is by itself, so you can clearly identify that with c. And you have t log a, mx occurring here. And because you have log a, and remember a is what you have to find, we can allow log a to be your gradient. And you can allow t to be x. Alright? And with that said, so that is like part 1. And part 2 now, if a graph of y versus x from the equation in part 1 is plotted, a straight line is obtained. State an expression for the gradient of the graph. Now if we have to represent this on a graph, this is what we're going to see. We're going to see, remember this is no longer your y-axis and x-axis. This will be a log v-axis. So log v will represent your y-axis and x will be t. This is your t-axis. In order for us to get that straight line, we have to put log v as our y-axis. We have to put t as our x-axis. You're going to get your line. The gradient will be log a. And the y-intercept, when it meets the y-axis, will be log k. Alright, so those are all the variables shown on a graph. So when they ask you to state an expression for the gradient of the graph for part 2 is simply log a. Part 1, when they ask you to use logarithms to derive an equation of the form y equal to mx plus c, this is your answer for part 1. For part 2, when they ask you to state an expression for the gradient, so part 1, the gradient here is a log a. So your gradient is equal to log a. Alright? So making sure we can recognize what is the gradient and what is the y-intercept. And even though they didn't ask this, I'll just use an example so you can see, for example, if we have to find k and a. Right? I'll just throw in a line with 2 points so you can see how to treat with it. Alright? Now suppose, now this wasn't given any question, right? But if they ask you to find k and a, just to show you how we can find k and a, because sometimes they'll bring the question where you have to find those values. In this case, all I wanted you to do is take the nonlinear and express it in linear form, which you did, and then recognize from that what's the gradient, which is log a. But suppose they gave something like this. Suppose they give you a line. Alright? This line, say, has, say this line, we have 2 points on this line. Suppose we have 2, 3, and we have 4, 6. Alright, or 4, 7. We have 2 points on that line. Good? Suppose the y-axis, of course, well, the y-axis now will be the log v-axis, and the x-axis will be the t-axis. Okay? So the y-axis is a log v-axis because we have converted it into a linear form. And the x-axis is your t-axis. Okay? And if they ask us to find a and k, how are we going to find a and k? Very important part of the question if they bring something like this. Good? So to find a, this is what we're going to do. The gradient of this line is represented by log a, right? We have 2 points on that line, 2, 3, and 4, 7. So we can find the gradient of that line using those 2 points. Let's get the gradient of that line using the same formula we are accustomed to. So the gradient will be what? This is what? 2, 3, 4, 7. So this wasn't part of the question, but I'm just showing, just in case they ask you to find A and K, what do? Your gradient is m y2 minus y1 over x2 minus x1. You label, this is x1, y1, x2, y2. You substitute into your gradient. Y2 is 7 minus y1 is what? 3. Over x2 is what? 4 minus x1 is 2. So you're going to get 7 minus 3 is 4. 4 over 2 is 2. So your gradient m is 2, and it means, look how we're going to get A. Look how we're going to get A. If the gradient is 2, it means the log A is also equal to 2. So if the gradient is 2, it means the log A is also 2. And therefore, we can easily find A. So this is how you can sometimes find A when dealing with conversion to linear, taking that non-linear form, converting it into linear form. The linear form is represented on a graph now. Remember, recognize what is the y-axis, the log v-axis now. The x-axis will be your t-axis. Log A will represent the gradient in this case, and log k will represent the y-intercept. So if log A is the gradient, and we worked out the gradient, we have 2 points on the line, and we worked out the gradient to be 2, then we can say log A is equal to 2. And if you have to get A now by itself, what are we going to do? If log A is equal to 2, log A is the same as log A to base 10. And if I have to get A by itself, what I'm going to do is move this from the logarithmic form to exponential form. Remember exponential form? If you're moving from logarithmic to exponential, take the base, allow it to become the base of 2. And then you just drop the log and leave A by itself. So it becomes what? A is equal to 10 squared. If that was the case, right? And therefore A is equal to 100. So that's how easy you can find A, if they ask you to do so, right? I just included it because they didn't ask it, but I just included it just in case they bring a question. All it did was to ask you to express it in linear form and recognize was a gradient. But if they brought 2 points and they ask you to find A and K, how do we find it? To get K, most of these questions will show you where it meets the y-axis. Good? Right? It shows where it meets the y-axis. But what you can do as well is, if it doesn't meet the y-axis, if you have a y-intercept, then it's going to be very easy. If you have a y-intercept, for example, suppose it met the y-axis at say 2. Suppose, I'm just showing here, suppose it met the y-axis at 2. We can get K easily. We're going to put log K equal to 2. Remember, log K now is a y-intercept, so we put log K equal to 2. And we simply move that from a logarithmic to exponential. Log K has a base of 10, and you can move that from a logarithmic to exponential. So that 10 comes up. K is equal to 10 squared, which is also 100. If the y-intercept was 2. Right? If the line met the y-axis at 2, or met it at some point, this is what we do. We take the log K, we put it equal to that value, and then we make K the subject by moving from a logarithmic to exponential. But there are sometimes cases where the line wouldn't meet the y-axis. Good? The line wouldn't meet the y-axis. You'll have these 2 points here. So how are we going to get the value of K? And this is what we do, right? What we do is this. So it's good to know it this way as well. So what we're going to do is this. We are going to, and I'll just erase here, so we can treat with that aspect of things. Or if not, let me see if I can. Right. So just to show, if we have these 2 points, we got the gradient as 2. How are we going to get the y-intercept? How are we going to get the value of K from log K? So what we're going to do is take the equation. We have log v is equal to log k plus t log a. Alright? Now you're accustomed when treated with an equation of a line y equal to mx plus c. You know you normally replace m with some value and you have to find c, not so? So m normally we know is the gradient. The gradient in this case of course will be 2. And to find c, we normally use a point on the line. You have 2 points. You just pick one. It doesn't matter which one. You just pick one. So let's go with 2, 3. All right. Now, normally to find c, you replace y with the y coordinate, and you replace x with the x coordinate. Good. Now we need to keep in mind we are using this equation here to help us to find c, which is a log k, right? But just writing down y equal to mx plus c, so you know you can bring back to mind how to find the equation of a line. Once you know the gradient and you know the coordinates of a point, you can find c and hence find the equation of the line. So we're going to implement the same process but using this equation of the straight line now, right? Which you just achieved by using logs, right? So this is what we're going to do. Keep in mind the gradient here will be log a. So I'm going to replace this m with log a. So m, the gradient, is a log a. Good? You have to also keep in mind every point here is not the x and y coordinates. Look at the axes. This is your t-axis. This is your log v axis. So this becomes your t coordinate and your log v coordinate. This becomes your t coordinate and log v coordinate now, not x and y coordinates. So you have to be very careful here. So t will be your 2 and log v will be 3. Because remember we're dealing with the t-axis and the log v-axis. So this is what we're going to do. We are going to replace a log v with 3. This is us finding log k, right? Which is your c. We're going to replace a log v with 3. We're going to leave a log k as is. Plus, we're going to replace t with 2. And we're going to replace the gradient log a with 2. So we're going to get here, right? Now remember I just made up this question, right? But I'm showing you the process. So we're going to get here 3 is equal to log k plus 4. I bring my 4 over, it becomes 3 minus 4 is equal to log k. I'm going to get negative 1 is equal to log k. Remember log k has a base of what? 10. And therefore to get k by itself, that 10 now will move from the what? From the base to the base of negative 1. And that will be equal to k. K will be 10 to the power of negative 1 or 1/10. So they're showing you sometimes they can bring a question like this. They can ask you to represent it in a linear form, and then they'll bring a graph with 2 points. If it cuts the y-axis, then, real easy to find k, right? You just put log k equal to that value. But sometimes if it doesn't and you have 2 points, then obviously you have to get the gradient, right? We got the gradient using y2 minus y1 over x2 minus x1. We got the gradient as 2. Good. And we have to remember, if we got the gradient as 2, good, we can use log a as our gradient to find a, which we did previously. A is equal to 100. But how are we going to get log k if you have 2 points on the line, if it doesn't need the y-axis? What you do is, Using the equation of the straight line, log v is equal to log k plus t log a. You allow log a to be your gradient, which is 2. You take any point on the line. I decided to go with 2, 3. Remember, 2, 3 is not your x and y coordinates. This is your t coordinate, which is 2, and your log v coordinate, which is 3. Very important. You're going to replace log v in the equation with 3 is equal to log k, which stays as is, plus you replace t with 2, and you're going to replace a log a with the gradient. Alright? Same way you're accustomed treating with the equation of a line, finding the equation of a line between 2 points. But don't let the log v, the t, and the log a confuse you. It's all based on the axes, carrying out the same process you're accustomed to. So this becomes what? 3 is equal to log k plus 4. 3 minus 4 is equal to log k. Log k is equal to negative 1. And therefore I can use my conversion from logarithmic to exponential to find k. So k is equal to 10 over 10 to the power of negative 1, or 1/10. So sometimes they can bring the question like this. Let's hope that they don't. But if they do, I want us to be aware of how to treat with such. All right? But thankfully in this question that here, all they ask you to just simply do is convert it into what? Linear form. Alright? Yeah? Yeah. Alright? Somebody asking? Oh, okay. Right? So what we're going to do, I am going to just take a 2-minute break, right? Just to sip some water. And what I'm going to do when we return, we're going to look at quadratic equations. Okay, so we're going to get into quadratic equations, looking at from completion of squares to rational inequalities, solving inequations, making sure you know types of roots as well, roots involving alpha and beta, making sure you can sketch functions, making sure you know your simultaneous of your linear and non-linear. And after that, we get into just some questions on APGPs, and then we look at quickly section 2. All right? Yeah? All right, so just a 2-minute, just 5 minutes, 5-minute break. Okay. Okay, so let us continue. So what we're going to do now, we're going to look at quadratics. So we know that question 2 of the exam paper will involve quadratics. You're also going to see APs and GPs. So let's make sure we can treat with such. All right, so the first thing we can see with a question involving quadratics is they can ask us to complete the square. So let's look at it. Right, so let's look at this question. So they can ask us to express negative 2x squared minus 7x minus 6 in the form a into x plus h all squared plus k. Now this is a common question you see in the examination. Let's make sure we can complete this square. Now, so to complete this square, I'm going to use, you know, there are two methods we can use. Well, we can use more than two, but I'll use the simple approach of the formula approach to help to quickly ensure that we understand the process, right? So I'm sure many of us would have understood the problem, the process, and can apply it. So if we have here f of x is equal to minus 2x squared minus 7x minus 6, and we want to express that in the form a into x plus h all squared plus k. So once they ask you to put this in that form, we know it's a method of completion of squares. So using the formula approach, there's a formula for h, there's a formula for k. So to begin, I'm going to let a be negative 2, b be negative 7, and c be negative 6. To get my h in my a into x plus h all squared plus k, h is found by using b over 2a. So b, it is negative 7 over 2 times a, which is negative 2. So you're going to get here negative 7 divided by negative 4, and b is equal to positive 7 over 4. So h is equal to positive 7 over 4. So we know that h is equal to 7 over 4. A is negative 2. We take that from the coefficient of x squared. B is negative 7. That is the coefficient of x. C is your constant, which is negative 6. And we use our formula for h. B over 2a. We replace b with negative 7. 2 times a with negative 2. And we got h. K, it is 4ac minus b squared over 4a. So make sure we know that formula. This will be 4 times a. I replace a with negative 2. I replace c with negative 6. Subtract. I'm going to replace b with negative 7 in brackets all squared. All over 4, I replace a with negative 2. So what are we going to get here? This becomes 4 by negative 2 is negative 8, and negative 8 by negative 6 will be plus 48. Subtract negative 7 in brackets squared will be 49, all over negative 8. So we're going to get here 48 minus 49 will be negative 1, all over negative 8. So we're going to get 1 8. So k is equal to 1 over 8. So having found h, so this is h, we know a, we know k. Let us put it in the form. It means that negative 2x squared minus 7x minus 6 in the form will be a, which is negative 2, open brackets x plus h, which is plus 7 over 4, close brackets squared, and k is positive 1 8. So that is us completing the square. Yeah, so putting it in a form. So make sure we know the formula for H, make sure we know the formula for K, and identify A, B, and C from the initial expression. Then they ask us to state the maximum value of f of x. Now, why maximum value? Because this is a quadratic expression. And if the number in front of the variable squared x squared is a negative number, then your curve will be shaped like this. So if A is negative, you're going to have a curve that is concave down, and you're going to have what? This will represent a maximum turning point. So once A is negative, your curve is concave down, and you're going to have a maximum turning point. If A is positive, on the other hand, then your curve will be shaped like this. It's concave up, and you're going to have a minimum turning point. All right? So in this case, our coefficient of x squared, the number in front of x squared, is negative. So we have a maximum turning point. Hence the reason why they're asking now for the maximum value. And what is the maximum value? The maximum value is always the y coordinate of your turning point. So just remember that. So the y coordinate of your turning point is your maximum value. So this is your maximum turning point. This point will have an x coordinate and a corresponding y coordinate. The corresponding y coordinate is your maximum value. And the maximum value, when we look to use completion of squares to recognize it, the maximum value or the y coordinate of the turning point is always denoted by k. So your maximum value, y, which is equal to k, is equal to 1/8. That's all for that question. So the maximum value is the y coordinate of the turning point. You can put f of x is equal to 1/8 if you wish. So f of x is equal to 1/8. That is equal to k. And so are we all clear on what was done to complete this square for part 1, to put it into the form? So it's going to be -2 can I see by short term? We're all clear on converting it into the form and also finding the maximum value. You all good? Short term, thumbs up. Right, nice. So let's also, state the value of x. State the value of x for which f of x is maximum. So to find the value of x for which f of x is maximum, that is asking you to determine what's the x coordinate of the turning point. So we know the y coordinate is 1/8. This is equal to 1/8. But what is the x coordinate of our turning point? So the x coordinate of our turning point is denoted by -h. So the x coordinate, which is the value of x, which is its minimum, is -h. H in this case is 7/4, so therefore the x coordinate of the turning point will be -7/4. Or we can take what we have inside here, x plus 7/4, put it equal to 0, and make x a subject. So x will be equal to -7/4. Or you can simply recognize it as -h. So that's -7/4. And then they ask us to use your answer in A part 1 to determine all values of x when f of x is equal to 0. So they want us to use our answer in part 1. So of course for this, let me just quickly show here. So far we know our curve will be, if it's -7/4, so let's assume -7/4 is here. The y coordinate is 1/8. Let's assume that's 1/8. So this is what we're looking at as our turning point. Good? So this here is the value of x, so which it is max, and this is the maximum value. Okay? 1/8. So let's use our answer in A part 1 to determine all values of x when f of x is equal to 0. Now if f of x is equal to 0, it means we are taking the quadratic expression, negative 2x squared minus 7x minus 6, and we're going to put it equal to 0. But remember, we converted that negative 2x squared minus 7x minus 6 into this form. And this is what they want us to use. So they ask us to use your answer in A part 1. Remember, A part 1 was this, where we had to convert it into that form. So A part 1 is taking negative 2, open brackets, x plus 7 over 4, close bracket, squared, plus 1/8. We're going to put that equal to 0. They want us to actually use the completion of squares method to solve for our two values of x. So how are we going to do so? The first thing we're going to do is remove k, negative 2 into x plus 7 over 4 all squared. Positive 1/8 will come across to the right as negative, positive 1/8, yes, comes across as negative 1/8, that's your k. We're going to remove negative 2 next. So to remove negative 2, we're going to divide both sides by negative 2. What I do to one side, I must do to the other. So negative 1/8 divided by negative 2. My two negative 2's will divide into each other to give 1. And I'm going to be left with x plus 7 over 4 all squared is equal to negative 1/8 divided by negative 2 is the same as negative 1/8 multiplied by negative 1 over 2. So I can invert that negative 2 over 1 to become negative 1 over 2. So I'm going to get x plus 7 over 4 in bracket squared is equal to positive 1 all over 16. And therefore, to get my x by itself, two more things need to be removed. I need to remove this power of 2 first. So let me remove that power of 2 by finding the square root of both sides. So this becomes x plus 7 over 4 is equal to the square root of 1 over 16. But we have to remember, when I find the square root of 1 over 16, I must consider both positive and negative results. So it means you have to put plus or minus in front of that square root symbol. When you find the square root, you must consider both. We often consider the positive because we have been trained to do so. But remember, you must consider the negative result as well. So we're going to get x plus 7 over 4 is equal to plus or minus the square root of 1 over 16 is the same as the square root of 1 all over the square root of 16. The square root of 1 is 1 and the square root of 16 is what? 4. And therefore, to get x by itself, x will be equal to plus or minus a quarter, and positive 7 over 4 will come across to the right as negative 7 over 4. And therefore, we can use our keywords, which are either x is equal to, we take positive a quarter minus 7 over 4. So we take the positive, which will give us negative 6 over 4 or negative 3 over 2. So that will be one root. That is why the curve will cut the x-axis at negative 3 over 2 or negative 1.5. And the other root will be, or x will be, we take negative a quarter this time, negative a quarter minus 7 over 4, which becomes negative 8 over 4, which is negative 2. So your roots are negative 3 over 2 and negative 2. So those are your roots, negative 3 over 2 and negative 2. Yeah? So what we want to do is, of course, they ask us to use your answer in A part 1 to determine all values of x. So we have determined all those values of x. Well, the two values of x by solving the quadratic equation, which are known as your roots. So let's move on to the next part. So they want us to sketch the function. So they want us to sketch the function f of x and show your solution set to A part 4 when f of x is less than 0. So they want us to sketch the function of f of x and show your solution set to A part 4 when f of x is less than 0. When f of x is less than 0, it makes it a quadratic inequality. And to solve that, we have to solve for a range of values, and we're going to use this sketch to help us to do so. So let us sketch the function f of x. So I'm going to erase here. Right, so to sketch the function, we need, this is part 5, and make sure we know this when we are sketching. If a sketch of a quadratic function comes in your exam, to sketch a quadratic function, you need one. So when you have to sketch the quadratic function, you need roots 1, which are otherwise known as your x-intercepts. And we have those. The roots are, we got them to be x is equal to minus 3 over 2 and x is equal to negative 2. Good? So we have those. We also need the y-intercept. Good? And the y-intercept is where your curve will cut or meet the y-axis. So it is going to meet the y-axis, and if you have your function ax squared plus bx plus c, the y-intercept is always denoted by c. So we have the quadratic function f of x is equal to minus 2x squared minus 7x minus 6. So c will be negative 6. So that's the y-intercept. So you know it's going to meet the y-axis at negative 6. What we also need to obtain or have when we are sketching will be your turning points. Or turning point. Right? So one turning point. And that turning point will comprise of your two coordinates you got previously in parts, I believe it was part 2 and part 3, which asks for the minimum value, which is the y coordinate of the turning point, which we got as 1, 8. And the value of x, the maximum value, sorry, which was part, I think it was maximum value. Let me just double check. Yeah, maximum value. Yes, maximum value. So the maximum value, which is the y coordinate of the turning point, is 1, 8. And the value of x, for which the maximum occur, we got that to be negative 7 over 4. All right? So the coordinates of our turning point we have. Okay? And if you want to express it as a decimal, no problem. That will be negative 1.75, and 1, 8 is the same as 0.125. And what we also need when we are sketching, we need the shape of the curve. And because our function, the number in front of x squared is negative, you know that your curve will be what? Your curve will be concave down. Yeah, so you know that's the shape of our curve. So we have all the information we need to sketch this function. So let's go sketch the function, and then let's use it to obtain the solution set. Okay, so right, so to sketch, let's see what we have. So just a simple sketch, doesn't have to be perfect on graph paper. So your simple sketch, y-axis, x-axis. You have your roots, which are, let's assume that this is negative 3 over 2 and negative 1.5. And you also have, let's assume that this is negative 2. So those are my roots. Good? We also have the y-intercept is negative 6. So you know it's going to meet the y-axis at negative 6. Let's assume that's negative 6 there. So this is my y-axis, x-axis. And it turns at negative 1.75. So we know that will be halfway. This is negative 1.75. Yeah. And negative 1.5, we have 0.125. Let's assume 0.125 is here. So we're going to have our value of x for which the maximum occur, negative 1.75. And you will also have your maximum value, which is the y coordinate of the turning point. Good? So that's where our curve will turn. And we know the shape of the curve, it is concave down. So this is what we're looking at here. All right, so that there is your quadratic function, okay? A sketch of it. But then they ask now to show your solution set for f of x less than 0. If f of x is less than 0, what this becomes now is a quadratic inequality. Okay, so it means that negative 2x squared minus 7x minus 6 less than 0 becomes a quadratic inequality. Now to solve a quadratic inequality, now all the hard work was already done. We have the sketch, and normally to sketch a quadratic to solve a quadratic inequality, you need the sketch to assist you in finding the range of values of x, right? The range of values of x. So how are we going to determine what are our range of values of x? Now we have our roots. Our roots are negative 2 and negative 1.5, which are very important when it comes to finding the solution set for a quadratic inequality. Less than 0, the inequality is less than 0 means we're looking at the region below the x-axis. So we're looking at the region below the x-axis. And once it lies, well, in this case it's below the x-axis, and once the mouth of the curve, one easy way to recognize where the range of values that satisfies the inequality lie, once the mouth of the curve is open, we do not shade in this region, we shade external. That's where our range of values will lie. The range of values that will satisfy this inequality. We're going to have values of x that are less than, if we're shading in this region, we are looking at values that will satisfy this inequality. Right, those values will be less than negative 2, x will be less than negative 2, or, I'm use or anytime it lies external, or me shading in this direction means x is greater than minus 1.5. So looking at all values that are less than negative 2 will satisfy this inequality, and all values that are greater than minus 1.5 will satisfy the inequality. So remember, when you sketch, you have to sketch normally to solve a quadratic inequality. We sketch the function. All right, they asked us to sketch the function, which we did. We highlighted the roots, we highlighted the y-intercept, we highlighted the turning point. But then they ask us now to show your solution set for f of x less than 0, which is a quadratic inequality. And to show your solution set will be a range of values. And to find those range of values that will satisfy this inequality, we look at the sketch. Less than 0 means we're looking at the region below the x-axis, Once the mouth of the curve is open, easy way to recognize it, where we shade, right? Once this mouth of the curve is open, you shade external. That's where your range of values will lie. Those values that will satisfy the inequality. So you can simply say here, x is less than all values in that direction will be less than this root negative 2. And all values in that region, of course, will be greater than the root negative 1.5. And that will be the sketch to represent the answer for that question. All right? So hope we're clear on what was explained here for that question. Yeah? Hope we're clear. So let's move on. We're going to move on now to right, I want to move on to a rational inequality. This is something you can also see in your exam, and let's make sure in question 1B or question 2, you can answer that question. Normally it's in 2A, or if not, sometimes 2B of the exam paper, in section 1 that is. All right, so let's treat with this. So to treat with this, what are we going to do? So that is known as a rational inequality. So they want us to determine the range of values. It's a rational inequality. What will also come into play will be quadratic inequalities, where again, we have to use a sketch to help us to find the range of values. Okay? So, to treat with this, what are we going to do? B. This is from 2017. 2x plus 3 over x plus 1 is greater than or equal to 0. Good? A rational is a fraction. So we have a rational here, fraction. And of course, we have an inequality symbol 0, hence making it a rational inequality. So to solve a rational inequality, what you have to do first is to remove it from its rational, from the fraction. And to remove it from the rational, you're going to multiply both sides by the square of the denominator. The denominator is x plus 1. So you're going to put x plus 1 in brackets squared. You're multiplying both sides by the square of the denominator. So this becomes what? X plus 1 squared times 2x plus 3 over x plus 1. And again, what I do to one side of the inequality, I must do to the other. Is greater than or equal to 0 times x plus 1 squared. And what is going to happen here? X plus 1 into x plus 1 squared becomes x plus 1. So I'm going to multiply x plus 1 by 2x plus 3 to give me x plus 1, 2x plus 3. Is greater than or equal to 0 by x plus 1 squared is 0. Now this here is, if I am to remove the, expand my brackets and simplify, I'm going to get a quadratic inequality. Okay? But what I'm not going to do is expand this. Right? I'm going to leave it as is, because if I expand it and I factorize it, I will come back to these two binomials. So it doesn't make sense expanding it, because at some point you'll still have to factorize the expression and you will come back to these two. So you leave it as is after you have removed it from the rational. You see, no more fractions. So what are we going to do? We are going to always begin by stating let x plus 1, 2x plus 3 be equal to 0. You allow it to be equal to 0 to get your roots. all right, to get your roots. So you're going to let that be equal to 0. I'm going to say either x plus 1 is equal to 0, x is equal to -1, that is one of my roots, or 2x plus 3 is equal to 0, 2x is equal to -3, and therefore x is equal to -3/2, or x is equal to -1.5. That's my second root. Okay? Having obtained my roots, what I'm going to do is, this is a quadratic inequality, of course. So to get the range of values, also remember with a quadratic inequality, to get your range of values, it's important to show a sketch. So that's a simple sketch. And my curve, you realize I've drawn my curve concave up, and I've drawn my curve concave up because if I expand these two binomials, I'm going to get a quadratic expression whose number in front of x squared will be positive. I'll get what? 2x squared plus 3x plus 2x plus 3. Number in front of x squared is positive. So I know when I'm sketching, I'm going to sketch a curve that is concave up. All right? So I have my curve which is concave up. My roots are -1. So -1 will be on this side, because -1 of course is greater than -1.5, which is on this side. So -1 is greater than -1.5. And where does my range of values lie? Now, because it is greater than or equal to, and again, if it's greater than or equal to, or even less than or equal to, you always shade your roots. All right? Now, greater than or equal to means I'm looking at the region. Where will my range of values lie? I'm looking at the region above the x-axis. The question we did before, it was a less than, right? In this case, it's greater than, so we're looking at the region above the x-axis. And once it's above the x-axis, and the mouth of my curve is open, as we see it's open, then my range of values will lie external to my mouth that is open. The range of values that will satisfy my inequality. And you can use test points as well. You can take a value that is less than -1.5, substitute it into that inequality, and you're going to see where it's greater than or equal to 0. You can take a value that is greater than -1 and substitute it into that rational inequality, and you're going to see where it's going to satisfy. You're going to get a value that is greater than or equal to 0. So in shading this direction, it means everything here is less than -1.5. So I can write, or x is less than or equal to -1.5. Or, and when it lies external like this, you use the word or, x is greater than or equal to -1. And that is me solving this rational inequality. So the first thing is to remove it from the rational, multiply both sides by the square of the denominator. Don't forget that. You'll end up getting here a quadratic inequality. Right? Do not expand. There's no need to expand. You just let each binomial be equal to 0. The purpose of allowing it to be equal to 0 is to get your roots. After you get your roots, you use a sketch now to get your range of values, because it's an inequality you're solving. So when you get the roots, you place the roots on the diagram. You know that your curve is concave up, because when you expand this, the number in front of x squared is positive. So you have a curve that's concave up. And because the inequality is greater than or equal to, greater than or equal to means you focus on the region above the x-axis. The mouth of the curve is open, so you shade external. And that's where your range of values will lie. And you can use test points. Just take a point less than -1.5, put it into the inequality, rational inequality, take a value greater than -1, put it into the rational inequality, and it's going to satisfy it. Which means that your range of values are right. And of course, you state it in the form showing what are the range of values. X is less than or equal to -1.5, or x is greater than or equal to -1. All right? So that is that question. Okay, let's look at next. Right, let's look at, right, we can look at roots involving alpha and beta. Well, let's look at some questions, roots involving alpha and beta, which you can also see in question 2, section 1. Yeah? So let's look at roots involving alpha and beta. So I'm erasing this. This you can also see in question 2, section 1. All right, so with roots involving alpha and beta, of course, there are a few things we need to ensure we recognize. We recognize the quadratic equation for these two roots, alpha and beta, and the quadratic equation is, so roots involving alpha and beta. So first recognize the quadratic equation, which is x squared minus sum of roots x plus product of roots is equal to 0. So that is your quadratic equation. X squared minus, the sum of roots x plus the product of roots is equal to 0. Which is equal to, we're going to write this as what? X squared minus the sum of your roots will be alpha plus beta x plus the product of roots will be alpha beta is equal to 0. Yeah? So first thing we must know. Secondly, we must also know that given a quadratic equation, ax squared plus bx plus c equal to 0, the sum of your roots, alpha beta, sum of the roots is equal to minus b over a. So this here represents the sum of your roots, it's minus b over a, and the product of roots, alpha beta, product of roots is equal to c over a. Alright, so two very important formulae we must know. What is the sum of the roots? What is the product of the roots? Yeah? And of course, our quadratic equation involving your roots alpha and beta. So let's shoot with this question. If alpha and beta are the roots of the equation 2x squared minus 5x plus 3 is equal to 0, they want us to determine the value of 1 all over alpha squared plus 1 all over beta squared. So we want to find the value of that. So what are we going to do? The first thing we need to do is identify what is the sum of the roots and the product of the roots given the quadratic equation. So we have a, which is 2, b, which is negative 5, and c, which is equal to 3. And we can get the sum of the roots from this. Alpha plus beta, using our formula, is what? Minus b over a. And we can work that out. This becomes what? Minus 5 all over 2, which becomes what? Positive 5 over 2. That is equal to the sum of our roots, alpha plus beta. The product of our roots, alpha beta, is equal to c over a. So c over a, of course c is equal to 3, is 2. So alpha beta is equal to c over a, or 3 over 2. But they want us to now find 1 all over alpha squared plus 1 all over beta squared. So they want us to find the result of that. So to find the result of that, this is where we're going to apply our basic mathematical principles of simplifying, and of course, some important rules we need to know for alpha and beta, roots involving alpha and beta. So let's see what's going to happen. If I'm to simplify this, the first thing I'm going to do is find my LCM. The LCM of alpha squared, beta squared will be one of each. Alpha squared, beta squared. So when I divide alpha squared into my LCM, alpha squared into alpha squared, beta squared, alpha squared into alpha squared is 1, and I'm left with beta squared, and I'm going to multiply beta squared by 1 to give me beta squared. Plus, let me divide beta squared into my LCM. Beta squared into beta squared is 1. I'm going to be left with alpha squared. And I'm going to multiply alpha squared by 1, which will give me alpha squared. Yeah? But then there's something you need to know about alpha squared plus beta squared. And sometimes to bring this proof, right? Because remember, if we have to solve this, we must be able to clearly recognize the sum of the roots and the product of the roots if you have to obtain an answer for 1 over alpha squared plus 1 over beta squared. Presently, I'm not seeing clearly alpha plus beta and alpha beta, sum of roots and product of roots. So what can I do to help me to clearly recognize these two? We need to know and note alpha squared plus beta squared is equal to, and make sure we notice, it is equal to alpha plus beta all squared minus 2 alpha beta. That is what alpha squared plus beta squared is equal to. And if you look at what alpha squared plus beta squared is equal to, we can clearly recognize sum of roots and product of roots in that expression for alpha squared plus beta squared. So I'm going to replace my numerator, alpha squared plus beta squared, with the expression shown. Yeah? Right? So I'm going to rewrite this as alpha plus beta all squared. That's alpha squared plus beta squared. I'm replacing it with alpha plus beta all squared minus 2 alpha beta over alpha squared beta squared. I'm not seeing alpha beta exactly by looking at it, but I can express it in a form that will allow me to easily recognize alpha beta. And for my knowledge of indices, I can write this as alpha beta all squared. All right, if you apply your laws of indices, power to a power, each one has a power of 1. If you multiply 2 outside by each one of the powers inside, we're going to get the alpha squared beta squared. So alpha squared beta squared is the same as alpha beta all squared. So my denominator, I can write alpha beta all squared. Let me substitute now into my expression. Now, what is very clear to me? I'm seeing alpha plus beta, which is clear to me, alpha beta, which is clear to me, and all I have to do now is substitute where I can find a value for 1 over alpha squared plus 1 over beta squared. Okay? So I've identified what is the sum of my roots, product of the roots, simplify the expression given. Of course, identify expressions that I need to know where I can clearly recognize sum of roots and product of roots. Alpha squared plus beta squared is what I have there. Alpha squared beta squared can be expressed as alpha beta all squared. And now let me substitute. This becomes what? This becomes alpha plus beta is 5 over 2 all squared minus 2. Alpha beta is 3 over 2 over alpha beta squared 3 over 2 all squared. So this becomes 5 over 2 all squared is 25 all over 4. Subtract 2 by 3 over 2 becomes 3 all over 3 over 2 all squared is the same as 9 over 4. So 25 over 4 minus 3 over 1, my LCM is 4. 4 into 4 is 1. 1 by 25 is 25. 1 into 4 is 4. 4 by 3 is 12. 12 from 25 will give me 13 all over 4. So I'm going to get 13 over 4 all over 9 over 4, which is the same as 13 all over 4 divided by 9 over 4, or 13 over 4 multiplied by 4 over 9. And of course, my two 4s can divide into each other to give 1, and I'm going to be left with 13 all over 9 as my result for 1 over alpha squared plus 1 over beta squared. So simply implementing sum of roots and product of roots. So I hope we're all clear on that. Yeah? Good? Yeah? Or battery low. Okay.